Okay, so hi everyone, welcome. So my name is Aurick. I'm going to be talking about Arctic Inference, breaking the speed cost trade-off in LLM serving. So this talk is going to cover some of the research and open source that we're working on in Snowflake. And it's the work of many members of the Snowflake AI team. Okay, so today, LLM inference systems need to achieve many different goals at the same time. That includes being responsive or having fast prefill speed in order to minimize the time, the time to first token. You want fast generation speed to improve the speed of the output tokens. And you also want to achieve high cost efficiency, which means maximizing the total throughput of tokens flowing through your system. However, existing systems need to make trade-offs between these goals. Analogy that we like to use is how gas cars can be either efficient but slow or fast but wasteful. And it wasn't until electric cars came along and was popularized that broke this trade-off. So the ambition of Arctic Inference is to be the electric car of LLM inference systems, which means offering high degree of cost efficiency, offering high generation speed, and offering fast responsiveness all in one system. So in pursuit of this goal, we built several new innovations into Arctic Inference that weren't previously found anywhere else. And we also open sourced all of our research in a ready-to-deploy system that you can find on GitHub. And I'll talk about that a bit later. So, rough overview of this talk, I'm going to cover a couple of the innovations that we worked on. So this includes some advanced parallelism techniques, optimizing generation latency, optimizing batch throughput, and how you can get started with Arctic Inference in our open source code. OK, so let's jump into advanced parallelisms. So fundamentally, why is it that existing inference systems have these kind of trade-offs? So one reason is because of inflexible parallelisms. So two of the most popular types of ways to parallelize your LLM across multiple GPUs, what's known as tensor parallelism and data parallelism. So in tensor parallelism, what we do is we shard the model across different GPUs, and then we process each request in parallel across those GPUs. So this is something that's going to get good latency or low latency because you're parallelizing the computation for that request across different GPUs. But it's often very bad for your throughput because it's going to incur a lot of coordination and communication costs between your GPUs. And on the other hand, data parallelism, what we do is we load the whole model on each and every GPU, and we send different subsets of our inference requests to different GPUs, and they are processed independently. So this is a process that's going to incur no GPU-to-GPU communication, which means that it's going to be very good for your throughput. But also, because you're only processing each request on a single GPU, it's often bad for the request latency. So as we illustrate in this diagram here, in terms of these three dimensions that we care about, the combined throughput, the prefill speed, and the generation speed, neither tensor parallelism nor data parallelism can simultaneously achieve the best in all three of these dimensions. And furthermore, real-world traffic, like ones that we observe very often in Snowflake, can be very, very bursty. And there are periods of high traffic and periods of low traffic. And that means that we really want our inference system to be able to dynamically adapt to each of these different periods of time. Right? So can we simply combine the benefits of tensor parallelism and data parallelism? Unfortunately, the answer here is no. And the fundamental reason is that they have different KV cache layouts. So the KV cache is the state that we have to keep in GPU memory in between generating each successive token. So to address this, what we do is we developed a new form of parallelism called Arctic sequence parallelism, aka Ulysses sequence parallelism. I think the previous speaker, Tunji, touched on that a bit. And in Arctic sequence parallelism, instead of sending different requests to different GPUs, we're sending different tokens to different GPUs. So this is something that's going to still incur some communication across your GPUs, but it's nowhere near as bad as what tensor parallelism incurs. And more importantly, the KV cache of Arctic sequence parallelism is exactly the same as for tensor parallelism. And this property allows us to build shift parallelism, which combines tensor parallelism and Arctic sequence parallelism. So during low traffic periods, what we do is we use tensor parallelism to minimize the latency of each request. And during high traffic periods, it can dynamically switch to Arctic sequence parallelism without transferring any KV cache because the KV cache is already compatible. And we can really quickly switch to data parallelism Arctic sequence parallelism in order to boost the throughput of the system. So data parallelism can achieve the best throughput, and tensor parallelism achieves the best generation and prefill latencies. Our benchmark shows that shift parallelism can essentially match the best latency that is achieved by tensor parallelism while still achieving high throughput. So we can see on this diagram here. So, and what's more is that shift parallelism adapts very well to these kind of real-world traffic patterns with periods of low traffic and periods of high traffic. So when we benchmarked shift parallelism on this workload trace, what we find is that shift parallelism is either the best or performs close to the best in terms of the initial response time, in terms of the generation speed, and in terms of the combined throughput throughout the duration of the entire benchmark through the high periods and through the low periods. OK, so maybe next let's talk a little bit about how Arctic Inference, what it does to improve generation latency specifically even further. So first, why is generation latency important? So recent LLMs, like the reasoning models, tend to think a lot longer to answer hard problems. And that means they generate a lot more tokens to answer each and every user query. Sometimes this can take tens of seconds, and sometimes this can take even minutes, right? And second, agentic frameworks nowadays can perform generation many different times in a loop. And this can drastically lengthen the time that it takes to complete the end-to-end task. For example, a coding agent might generate some code and then repeatedly refine that code until it passes some set of tests. Right? So you might tell it to write a program, and then it'll write that program, and it'll run it, it'll see some errors, and then it'll go back and fix some lines of code, and it'll go again, and on and on. OK, so to accelerate this generation latency problem, Arctic Inference implements speculative decoding. So this is something that's been around, and so this is how roughly it works. So normally, without speculative decoding, when we receive a prompt, the large language model will predict one output token at a time. And this output token is going to be fed back into the LLM in order for it to predict the second token. And that second token is fed back to predict the third token, and so on. So this happens one token at a time, and each time we predict one token, we need to run a full forward pass of the model. So in speculative decoding, it improves this by first taking a quick quote, guess at what those next n tokens might be. And then the LLM is able to essentially verify those n tokens in parallel in one pass of the model. So this means that we can actually generate multiple tokens in each iteration of the model. And this can greatly speed up the generation speed. So the question now is, how do we generate the actual guesses? So in Arctic Inference, we use a pretty simple method. We use a different lightweight model. And this model is kind of attached to the end of the LLM and uses the hidden states outputs from the LLM. And it uses those states to predict the next few tokens. And the particular model we actually use is actually an LSTM, which is very small and fast. And we found this method to be simple, but also very effective. OK, so for even more effective speculative decoding on agentic applications, we developed a method called Suffix Decoding. So this is based on the observation that LLM agents often generate very long runs of repeated or similar text. And this repeated or similar text should be easy to speculate, right? So for example, in the previous example, a coding agent might generate a new block of code where only 1 or 2 lines of that code is changed from the previous time that code was generated by the model, right? So to leverage these repetitive patterns, what suffix decoding does is it builds a cache of previously generated outputs, and it organizes this in a suffix tree, which is very efficient. And it uses the suffix tree cache to aggressively speculate new tokens when it detects that there is a repeat that's happening, right? So this approach can actually speculate sequences that are tens of tokens or even hundreds of tokens long. And it can do this very, very rapidly, at around 5 microseconds per speculated token, which translates to around like 200,000 speculated tokens per second. And it's doing this on a single CPU, right? So if you have even more CPUs, it's like scales up from there. Suffix decoding is actually going to appear as a spotlight paper in Europe later this year. So for those who are interested and are going to that conference, definitely visit our presentation there. OK, so a further technique that we recently explored is combining both the Arctic LSTM speculator and suffix decoding in order to try to achieve the best of both worlds. And essentially, suffix decoding is good at speculating these long sequences when they're pretty obviously repeating from before. And then the LSTM speculator kicks in when there's little repetition or no repetition detected, so it needs to make some more precise predictions on what the next few tokens need to be. And the implementation for doing this is actually pretty simple. So basically, at every single generation step, we query suffix decoding to see if there is a repetition that's happening. And if there is, then we use the suffix decoding speculated tokens. And if not, then we default back to running the LSTM speculator. OK, so with speculative decoding and suffix decoding, we can boost generation speeds by 2.4 to 4x across a variety of different workloads. So these include agentic tasks, Sweetbench, open-ended chats in ShareGPT, more simple coding in human eval, and as well as like mixtures of all of these different types of requests, right? In particularly, it achieves like 4x improvement for the agentic Sweetbench task. And this is because this is one of those like highly repetitive kind of tasks that suffix decoding is very, very good at optimizing. So we also trained speculative decoding models for the GPT OSS model, and we showed that there, even for these more recent models, we can achieve like a 1.6 to 1.8x faster generation. OK, so another interesting observation that we made is that this combined speculator can actually generalize very, very well to longer contexts. And longer context is actually quite important for a lot of practical tasks where you want to put a lot of useful information into the prompt of your LLM. So this graph here is showing the acceptance length on the y-axis, which is essentially a measure of how many tokens were guessed correctly at each step, and the context length of the request that we're sending on the x-axis. So we tested a model called Eagle 3, which is a pretty recent state-of-the-art speculative decoding technique. And we found that it actually degrades pretty rapidly as the context length increases, which is kind of interesting. But also, when we tried our combined Arctic Speculator, it actually works very, very well, even for the longest context lengths. OK, so maybe next, I want to just show like a quick demo, I think, to show the speed of like speculative decoding. So on the left-hand side, we have like the baseline inference system running in vLLM without speculative decoding enabled. In the middle, we use speculative decoding in vLLM with our LSTM model. And on the right-hand side, we're running suffix decoding on a highly repetitive query, right? So we generate some highly repetitive queries there. OK, so let me see if I can actually run this. I'm not too sure how to move my mouse. OK. All right. OK, yeah, so the suffix decoding side is already done. And we can see the speculative decoding is faster, and the case without speculative decoding is still running, right? So maybe I'll just drag it back and run it again in case you missed that. OK, so here we go. OK, yeah, and it's done. All right, so OK, let's move on. OK. Yeah, let me, I forgot how the, up there, OK. Let me just wait till this one finishes. OK, are you ready? Yeah. OK. And yeah, it's done. So on this right-hand side, I think like you would kind of expect this kind of speed in like a very highly repetitive scenarios, where if it's a more like open-ended, hard to predict kind of scenario, like the middle column would be like more what you would expect from speculative decoding, right? OK, so next, I'll talk a little bit about how we're optimizing batch throughput. So batch inference. And I'm going to go a little bit faster through here. So batch inference involves running a prompt over a large number of documents or database rows. So some of the common use cases that we observe a lot in Snowflake include text classification, sentiment detection, summarization, and embeddings. So instead of latency, batch inference is only really sensitive to the total throughput in terms of the raw number of tokens that we can process per second, right? And another important characteristic is that batch use cases typically receive a lot more input tokens than output tokens. And what we see in Snowflake is roughly like a 10x more input tokens than output token kind of distribution. And what this also means is that because there's so few output tokens, that what we previously talked about, which is speculative decoding, is going to be a little bit less effective here. So to optimize the input token throughput, we take a slightly different approach that we called SwiftKV. And this approach actually changes the model architecture itself so that input tokens only propagate through halfway through the model. So for example, if this LLM here had 6 layers, all the input tokens that are being processed would stop after the 3rd layer of the model would be processed, while the output tokens still run through the rest of the model. And this will effectively reduce the computation of the input tokens by half, and while the computation for the output tokens remains unchanged. OK, so after applying this transformation, if you actually just try to run the model as it is, what you'll find is that the accuracy of the model is actually much, much lower than before. And this is not really surprising because we actually just changed how the model is wired together. And namely, we changed how the KV cache for the later layers are computed. So after applying this transformation, what we do is we recover the model accuracy by distilling the model from, distilling the transformed version of the model from the original model itself. And during this distillation, we found that it's enough to just train the Q, K, and V projections of the later layers. So we're not distilling the whole model, but we're only distilling like these small parts. And these small parts account to like less than 5% of the parameters of most models, right? And this means that this distillation procedure is actually very, very cheap. And we can run it very quickly on a single node, and it takes less than 1 billion tokens of data to recover the accuracy of the model. So when we did this, the transformed models are actually performing very, very close to the original model quality when we measured it across a spectrum of different benchmarks. And more importantly, for batch inference, SwiftKV improves the throughput by 2x. Which leads to pretty massive speed and cost savings. OK, so SwiftKV also is a research paper that we worked on that's going to appear in EML NLP this year. So if you like to learn more, I can share the paper with you, or you can see us at that conference. OK, I'm gonna skip this part and just jump straight to the Arctic open source. So basically, like everything I talked about is in open source. And so, just to summarize, Arctic Inference is a fast and cost-effective inference system. It combines a lot of research innovations that we worked on in Snowflake, and that includes shift parallelism, speculative decoding with the LSTM and suffix decoding models, and SwiftKV. And when all these innovations are combined, it can significantly improve the end-to-end response latency and the overall throughput of the system. It's also open source, and yeah, like everyone can try it. And getting started with it is really, really easy. So Arctic Inference, we built it as a vLLM plugin. So what this means is that you just install Arctic Inference with pip. And then this functionality becomes automatically available in your installation of vLLM, right? So you can still launch vLLM and run vLLM using the same familiar commands like vLLM serve. You add this environment variable here to enable Arctic Inference, and all of a sudden you have all of these additional configurations that you can use to enable the Arctic Inference features like shift parallelism, suffix decoding, and SwiftKV. OK, so next, we also provide a very easy-to-use system and recipes that you can use directly to train your own SwiftKV and Arctic Speculator models. And this is in a project called Arctic Training. So Arctic Training is a sister project of Arctic Inference. And it's built to be flexible, and it's built to be hackable for researchers. So end-to-end training runs in Arctic Training can be encoded in a single YAML file, so they're completely reproducible. And it's also fast and scalable because it's built on top of deep speed. So you can train SwiftKV and Arctic Speculators in Arctic Training by customizing the example recipes that we already provided. And these trained models can be deployed directly in Arctic Inference. OK, and with that, check out these links if you're interested in these projects. Happy to take any questions. Oh, this one. No, this one's not with a repetitive data set. So the data set we use here is we took wild chat, which is like this collection of like open-ended chats collected from ChatGPT users. And we bucketed wild chat in terms of the user prompt sequence lengths, and then we ran those prompts, right? Mm. Yeah. Right, right. So this case is with a low batch size. I think we performed this experiment with a batch size of 1, and also like the y-axis is the acceptance length. So this is a metric that's not going to change depending on like the batch size that you use, right? As for why the result looked like this, actually we were also very surprised. We also, one thing we tried was we took the published Ego3 models and we also took long context data and we trained it specifically on long context data and then we re-evaluated it. So those results look a little bit better than here, but it's still like you can see some degradation, right? So I think it's a pretty interesting question why that is. Oh, so the question is if we have a pure CPU system, would Arctic Inference work? So I think, so first of all, I think we primarily wrote the Arctic Inference code assuming a GPU system. Some of the research techniques, I would say, could work in a CPU-based system. For example, SwiftKV, right? If you're running a model on the CPU or GPU, if you're just skipping half the model, then that's going to work whether you're on a CPU or GPU, right? But we have not tested if this is going to work out of the box with the current like SwiftKV code in Arctic Inference. Yeah.
Question. So for the suffix decoding case, like, did you guys try anything like on-the-fly training of it for agentic systems?
Oh yeah.
What's repetitive is difficult to say.
Yeah, yeah. So I think so. The question is, did we try any kind of like on-the-fly kind of training for suffix decoding? So I guess there's like two parts, right? Like you could use an alternative form of speculative decoding and do kind of like online training. So typically, that's actually a little bit challenging to implement. So as far as I know, there are not really any like really popular inference systems that implement that. And second of all, yeah, like in suffix decoding, essentially when you're caching requests, you're essentially like quote training the cache to do better predictions based on the previous requests, right? Yeah. Okay. Yeah. Well, I'll hang around here in case anyone else have any questions. And yeah, thanks everyone for being here.